fifth lecture on this topic of semiclassical interactions of light with matter, looking at a two-level quantum system and its interaction with light in different facets. In the previous lecture, we also derived the optical Bloch equations and argued that the optical Bloch equations gave a very convenient mechanism to describe how the population of the coherences in the density operator change for the application of optical pulses. And we also looked at this really interesting idea of the correspondence between the strong and the weak field limit case, and discovered that if with time we were to plot the, say, the populations in the excited state for resonant light fields which are intense, we obtain an oscillatory function on resonance without detuning, which went all the way up to 1. Okay? And it kind of kept on oscillating between 0 and 1. So this is continuous oscillation between the ground state and the excited state. And I'll give you a homework problem to determine what the coherences would be as a function of time as well in this case. What is this case called? What is this phenomenon called? Rabi oscillation. This is perfect on-resonant Rabi oscillations. Okay? There is also going to be an evolution of the coherences rho AB, and that will be a homework problem associated with this inversion between the excited and the ground state. And it's a continuous process. Then we discovered that if we were to add damping to the system, and we introduced this damping parameter gamma and wrote the Bloch equations for this, then we discovered that these oscillations damp out. Even if we are in the on-resonance condition, these oscillations damp out and finally they reach a steady value. Okay? This steady value cannot be greater than 1/2. Okay? And in the limit of very large damping, these oscillations are barely seen. Okay? And one gets just a smooth approach to some intermediate value perhaps, which is called the weak field limit. And in the weak field limit, we also in one of our lectures derived the Einstein B coefficients. And from there guessed out what the Einstein A coefficient would be. So if we factor in damping, these Rabi oscillations are they dissipate, and it becomes harder and harder to see these oscillations. Correct? Okay. Now the question is that we do know that this kind of approach to a steady state value, let's call this saturation. Now let's look at saturation in a bit more detail, because saturation is also related to absorption and it's also related to experiments. So let's look at this phenomenon of saturation to in some greater detail. So do you have any questions about this from our previous lecture? Now, we do know what the optical Bloch equations are. They go as follows: E by dt, U, V, W. These are also the axes on the density operator, corresponding to the x-axis, the y-axis, and the minus z-axis. And we know that this is given by Rabi frequency. Remember always that the Rabi frequency omega r is given by some mu AB E naught over h bar. Correct? So the Rabi frequency is proportional to the electric field. And the electric field determines the intensity of the light beam that is shown onto the atoms. The intensity, by the way, of a nice circular beam is proportional to E naught squared. Okay? This is given by half refractive index speed of light epsilon naught E naught squared. Okay? This comes from the Poynting vector from electrodynamics. Anyway, so the optical Bloch equation goes as follows: delta R, the detuning factor, cross product with U, V, W, minus the damping term, right? Gamma, U, V, 2, W, plus 1. Optical Bloch equations. Now what's going to happen in saturation? So these plots are solutions to the optical Bloch equation for different ratios of gamma and omega r. Okay. Now what happens in saturation? In saturation, everything is steady to some final value. Okay. That final value would be achieved when the left hand side of this equation is 0. So let's find out the saturation value for the inversion parameter. And from that we derive the saturation value for OBB. Okay, because this W is related to the inversion between the excited and the ground state. So let's find the saturation value for W to begin with. So we put the left hand side equal to 0 and we get 3 algebraic equations that we need to solve. I give you 5 minutes or so to find out, write down the 3 equations and determine the saturation value of W. So don't be confused this omega and this W, right? Okay. So these are the steady state values of U, V and W, right? So we solve these 3 equations and find out W. Okay. So if you do a little bit of algebra, W infinity, which is the steady state value of W, comes out as minus 1 - V और W तो eliminate हो जाएंगे, 3 equations है ना, so V and we want to eliminate V and U. You can find out the steady state value of V and the steady state value of U as well, but we are interested in the steady state value of this inversion parameter. Alright? So this is our steady state inversion factor. Now if I kind of, what else can I do for this? Let's call this factor S. Okay? X is omega r square over 2. What is this kind of, what is representing this factor? What is omega r square over 2? Physically, what does it mean? It's a Rabi oscillation square, but physically, what does it, where does it come from?
Magnetic moment into electric not.
How strong an electric pulse do you apply? How strong a light field do you apply? The intensity of the incident radiation. And it also depends upon internal parameters of the system, which are captured by the electric dipole moment element. Between which levels a transition are you assuming? Right? So this is the strength of the applied field. And this is divided by a detuning factor. How far off is your electric field from the transition that you're interested in, plus damping. So this is S. This is called, let's call this a saturation factor. Okay? Saturation factor. Yes, please.
मैट्रिक्स एलिमेंट निकालने के लिए हमें वेव फंक्शंस को इंटीग्रेट करना होगा।
जी, हमें पता होना चाहिए कि किन दो वेव फंक्शंस के दरमियान बात कर रहे हैं। एक होमवर्क प्रॉब्लम इसके मुताबिक भी है, ठीक है? So remember that this S, so this is some instant intensity, right? And this is a damping parameter plus some G tuning. Okay, so do keep this in mind as well. एक मिनट. If I eat the well, again, steady state में, this is the steady state value. Okay, so all of these are steady states now. Right? Alright, so now let me tailor this a little bit. Sigma r square over 2 divided by gamma square one plus delta omega over gamma square. Okay? So just recast this fraction into this form. So this numerator is S when delta omega is 0. This numerator is S when delta omega is 0. So let's call this numerator S naught, which is S when delta omega is 0, which is so S naught is a resonant saturation factor divided by 1 plus delta omega over delta whole square. So this is S. So W infinity the steady state W is minus 1 plus S right? But S is this vector. S is given by this as well. So we write S as S naught 1 plus delta omega over gamma whole square. Alright? Where S naught is given by R square over 2 gamma square. Correct? Now this S naught, the numerator is proportional to the incident intensity and gamma square is proportional to some factor which is specific to the atom because there's a damping in it. So this is a ratio of two intensities really. Okay? So I can put this equal to the intensity of the incident light normalized to some other intensity which is specific to the atom. ISAT. Okay? So now these are my very kind of nice relationships. What I could do now, what I'm interested now is finding rho BB at infinity. What is this equal to? Delta plus 1 over 2? W plus 1 over 2? Because my W is rho BB minus rho AA, which is 1 minus rho BB. This is 2 rho BB minus 1 is W, so my rho BB is 1 plus W over 2, right? So my rho BB at long times is given by 1 plus W divided by 2. Okay? So it's given by half 1 minus 1 plus. Okay? This is half 1 plus S, 1 plus S minus 1. So this is half S 1 plus S. This is my rho BB at infinity, right? So this is really 1 half. S is S naught divided by this. S is S naught divided by this. S naught I think this is what it turns out to be, right? Correct? So this is the steady state population. S naught is some incident intensity. It is representative of how much light are you putting in onto the system. And this can give you the steady state values for weak and the strong field limits. So if the S naught is large, which means the incident electric field is large, you put in large amounts of light, then S naught will be larger than this factor. The field is larger than the damping. So S naught will overwhelm this, it will overwhelm this, You have S naught in the numerator and S naught in the denominator. So the strong field limit case, this population inversion will approach 1/2, right? Strong field limit case. And we've also seen this from other mechanisms, right? Remember, there is some non-zero damping in the system. Okay, so in the steady state, when there are no changes in the excited populations, the maximum you can achieve is 1/2. And in this case, this is saturation. You apply strong electric field onto the matter. That strong electromagnetic radiation is causing absorption. Okay? And whatever is being absorbed is then coming down through stimulated emission. So, in a sense, no light is no exchange of light between the atom and the incoming radiation is taking place. Whatever is being absorbed is being emitted. And this happens when the ground and excited state populations become equal. And that's what rho B B1/2 means. Saturation of an atomic level, two-level system, saturation of atom means that there's an equal population between the ground and the excited. There is dynamic equilibrium. Spontaneous emission is very weak as compared to stimulated emission. Okay? So absorption and stimulated emission become equal, and both of them are much larger than spontaneous emission. This phenomenon is called saturation. Right? Yes, please. हमने कहा कि S not large है. If S not large है, तो S not is larger than this. We ignore this term and we ignore this term. We have S not over S not.
लेकिन हम S not को किस बेसिस पे लाते हैं?
क्योंकि S not ये है, ये incident intensity. So a strong electric field is incident on the atom.
और ये saturation का जो केस है, ये सिर्फ तब होगा जब detuning हम कंसीडर करें.
जब
detuning को कंसीडर करें.
दूसरे केस में भी होगा. देखो, अगर दूसरे केस में भी होगा, किसी भी केस में हो सकता है. डैम्पिंग होनी चाहिए. ठीक है? अगर डैम्पिंग नहीं है, so you do not achieve saturation, you achieve Rabi oscillations. ठीक है? If you have even a tiny bit of damping, these oscillations will eventually zero down for over longer periods of time to 1/2. You get it? ठीक है? Alright, so now let's look at the other extremes. So if in the weak field case, when S naught is really small, so what happens in that case?
Zero.
So rho BB becomes 0. So in the exact opposite limit, S naught is, if it approaches 0, this becomes 0, whatever is in the denominator doesn't matter, this becomes 0, and rho BB becomes 0. There is no excitation whatsoever. Okay? If gamma is really large, damping is large. So let's assume that. So either in the weak field limit or when gamma is large. When gamma is large, and the field is weak. Gamma.
Field weak enough as you know.
Gamma is large. Huh? The field is weak. This is 0, right?
प्लस वन लगा के जब तक जीरो ही होता
क्या?
as long as plus one is there फर्क नहीं पड़ता
Gamma is large. Right. By the way, if delta omega is large, if delta omega is large, and if it's overwhelmed other things, even then rho VB will be 0. Okay? So in the weak field limit, when S approaches 0, rho VB approaches 0, and rho AA will approach 1. Right? This is the weak field limit case. Okay.
अगर डैम्पिंग है ही नहीं तो वन आ जाएगा राबी ऑसिलेशन आ जाएगी जैसे
Then we will have this formalism will not apply because you will never get the left hand side equal to 0. So this assumes that you have achieved saturation, alright? This is for the saturation only. Now what you would like to see is photon scattering. How do we see an object? So now with this idea of saturation that is in front of us, we can of course determine the steady state values for the excitations. How do we see an object? We see an object when light falls on it and photons are scattered. So now we would like to see atoms. Say we have a cell evacuated in which we put in atoms, right? And these are two-level atoms. And we shine light on it. Some incident electric field is coming in, right? With some intensity. Now we see this object because photons are being scattered from this object. So if we have a detector, right? Some detector D, which is placed sideways, if photons are scattered through spontaneous emission, sideways, because spontaneous emission photons will come sideways. So if you want to see these atoms from the side, you have to see photons that are scattered by spontaneous emission from this process. And the rate of spontaneous emission actually depends upon the excited state populations. Correct? So if we want to find out the rate of scattering of photons, okay? So from this ensemble of atoms, so we have n atoms, right? And want to find out how many photons are being scattered, and we would like to find out the rate of those scattered photons. Let's call that rate of scattered photons this symbol gamma. Okay, so this is gamma. Now there is a decay rate associated with each excitation. That's called small gamma. And then there are populations in the excited state. So this gamma is really equal to the scattering rate of a single photon multiplied by the population, the element which corresponds to the excited state population. Right? So in steady state, this will be given by this, okay? This is the decay rate of scattering of a single photon from a single atom. This is the fraction of atoms which is in the excited state. So you multiply the two, you'll get the total number of photons that are coming from this ensemble of atoms per unit time. Okay, so this is a photon scattering rate. You'll be able to see an object if this is non-zero. Correct? So now we already have a formula for the saturation excitation, rho BB. This is excited state probabilities. The population is in excited state. Rho BB is given by the formula that we have over there, right? So our photon scattering rate, which is actually determining the visibility of these atoms, is given by gamma times rho BB. So it's given by gamma over 2 S naught. S naught plus delta omega over gamma squared plus 1. This is the photon scattering rate. जी
gamma की इस इक्वेशन से कैसे पता चलता है कि फोटॉन स्कैटर हो गए? लाइक हमने डिके रेट और हमने नंबर ऑफ इलेक्ट्रॉन्स इन एक्साइटेड स्टेट को मल्टीप्लाई कर दिया. हाउ डज दैट डिटरमाइन द फोटॉन इस इक्वेशन से स्कैटर हो गए?
देखो, if you have an electron in the excited state, right, it comes down, it has a lifetime of 1 over gamma. We're considering spontaneous emission. It has a lifetime of 1 over gamma. So the rate of decay of an excited state is gamma. But if there are no excited populations, if the population of the excited state is 0, no matter what gamma is, you cannot get any photons out. So you really have to multiply the decay from a single excitation with the number of excitations. You get the total number of scattered photons per unit time. Okay, now if we look at this expression over here, we kind of try to make some simplifications to this. First of all, there is a maximum limit to this scattering rate. Suppose we are exactly on resonance. Right? So this is the on resonance condition. Okay, if this is true, then this term becomes 0, and we have gamma over 2 S naught divided by S naught plus 1. Okay. If S naught is large, which means large intensities, so if we have large intensities shining onto these atoms, okay, and the incident radiation is perfectly on resonance, then S naught will be much larger than 1. Gamma will achieve maximum photon scattering rate. At maximum photon scattering rate will be gamma by 2. This is the maximum rate at which we can receive photons from this gas of atoms. Okay? So if you're counting how much light this detector is receiving, we can't go beyond this. Whatever is present, the decay that is present inside an atom, that limits how many photons we receive. Okay? So now all of this has very strong implications for detection and doing experiments. Okay? Now we also would like to kind of see what is the dependence of the scattering rate on delta omega. Okay, so consider this experiment. You have this cell of atoms and you're shining light onto this, okay? And you have a detector here. And you want to see how much light is being emitted from these atoms. So you're really collecting the scattered photons in a particular angle. And these are spontaneously emitted photons. Now what you would like to do is, you'd like to find out the brightness of the atoms, for example. How many photons are they scattering? So what you have one element in your control. So you keep the incident electric field fixed, which means the incident electromagnetic intensity is fixed. But you have a detuning factor at your disposal. You can change the frequency of the incident light. So what you would like to do, I would like to plot this gamma as a function of delta omega. That's what I'm really interested in for the time being. But remember that my S naught is given by this. And then this is constant. So my incident electric field is constant, my damping is constant, it's given by the atoms. So I want to plot this gamma as a function of delta omega. Right? As a function of detuning. That's what I want to do. Yes, yes. Okay? So let's try to do this. Okay, so why am I interested in S naught? Because S naught also has a gamma in it. So it also depends upon what gamma do you choose. So S naught has a gamma in it, and there's a gamma here as well. So I would like to replace this. I would like to explicitly know what the gammas are as well when I plot this. Okay, so let me try to do this on Mathematica. Okay. What will be the scattered photon intensity? How many photons will I detect between time? Right? And from that I can also measure the resonance frequency of for these atoms. Let's see how. Capital gamma for various values of S naught. Okay? The blue curve is for 1 unit of S naught. S naught, remember, is determined by the incident intensity and the damping. Okay, so I keep the incident damping fixed and change the damping factor gamma. Or I can keep the damping factor fixed and change the incident intensity. So this blue is the smallest S naught. The brown is 10 times the S naught, which corresponds to 10 times the S naught is 10 times the incident intensity, or 10 is square root 10 times the damping factor, right? So S naught is being changed here. And you observe that the photon scattering rate is higher when the incident intensity is higher. More light shines in onto the system, more photons are scattered. That's the green curve at the top. That has 100 times S naught, 100 units of S naught in that green curve. The middle brown curve has 10 units of S naught. And the blue curve is just 1 unit of S naught. And this is the detuning frequency. So you move further away from the resonance frequency, no photons are scattered. Okay, because there is no absorption of photons. And none of this could be scattered. Rabi will be very small. Okay? So if away from resonance, delta omega is large. Look at the top boxed expression over there. Delta omega is large, rho B will begin with to be scattered. There are no excited populations. Okay? So the photon scattering rate will be very low. So you're far away from resonance, you're highly detuned, the scattering rate drops. Okay? But for the green curve, there are still some scattered photons, because you began with shining. This is a brute force approach. You shone in a lot of laser radiation onto the atoms. But my question is, if you would like to use this data for determining the resonance frequency of these atoms, omega naught, would you like to use a stronger electric pulse or a weaker electromagnetic pulse? आप इस कर्व को देख के बताएं। Weak, क्यों? The peak is sharper. So this seems counterintuitive. If you would like to find out the resonant frequency of a gas of atoms, you shine laser light onto it whose frequency is variable, wavelength is variable, and it's counterintuitive that you would like to use a fainter beam to do that. The fainter beam, you will get less scattered photons, less scattered radiation. However, you will be more precise. Your sensitivity onto the position of the peak will be higher. So you'll be able to measure the resonant frequency of this gas or atoms with a higher precision if you shine a weaker pulse of light onto the atoms. So these scattered photons are actually going out in all directions because these are spontaneously emitted photons and you're just detecting a fraction of them. Okay, so this is how you see objects. So if you have laser light and it just shines off in vacuum, you'll not be able to see any beam of light. All that light is actually coming from scattered photons. This is how you see the particular colors in the sky. This is why you see that the sky is blue as well. So all of these photons are being scattered by some mechanism. Okay, so this idea of saturation gives you a good idea of photon scattering rates as well. And another thing that you will observe is that so you have a switch that changes delta omega with time. So with time, first of all you see hardly any photons. Then when you approach resonance, you will see a large peak, and then you go away from resonance, you detune again. You're blue shifted and you red shifted, you see less photons. You're on resonance, you see large number of scattered photons and so on. Okay, so this is fluorescence of atoms. This phenomenon is called fluorescence because you shine light, that light excites the atoms into a higher level. And those atoms, after a certain characteristic lifetime, they decay back and immediately give you photons. This phenomenon is called fluorescence. So this is the laser fluorescence of atoms inside a vapor cell. Laser fluorescence. Now, in fact, the same idea of photon scattering can also be used to find out how an ensemble of atoms absorbs energy. You see, when light is being shown into this ensemble of atoms, photons are being scattered, which means energy is going to the left and to the right. Less energy is available for the atom to come out because of these scattered photons. Right? So the intensity of the outgoing radiation will be smaller. So these scattered photons also cause absorption inside the system. And we can actually determine this absorption. That absorption will be a function of this photon scattering rate as well. The absorption will be proportional to the photon scattering rate. And the absorption will also be dependent on the frequency. Right? Because this is dependent on the frequency. This is dependent on the frequency here, right? So the absorption is also frequency dependent. In fact, I can look at the absorption from a slightly mathematical perspective. So suppose I have this cylindrical section of atoms and there are n atoms per unit volume. And this cross-sectional area is, say, A. This length, suppose, is Z. Okay? So, what I would like to find out is how much power is being absorbed by the system. So, I input light, electromagnetic radiation, some incident intensity I incident, right? First of all, I want to see how much energy is being absorbed. That energy that is being absorbed is actually the scattered photon rate, right? So this absorbed power will be given by the photon scattering rate times the number of atoms in the system. Correct? And how many atoms are in the system? N A Z. Let's call this BZ, right? Small is BZ. Is that it? Very, very small. Is that it? That's it? Photon scattering rate. How many photons are scattered per unit time? The number of atoms in the system. What else?
प्रोटॉन स्कैटर तो हर डायरेक्शन में होता है ना, सिर्फ एक लिनियर पाथ में नहीं होता।
हमें से कोई गलत नहीं, लेकिन हमें तो एब्जॉर्प्शन कहते हैं जितने भी होंगे।
सही है, हाँ।
ये पावर है, याद रखें, दिस इज जूल्स पर सेकंड। और क्या चीज चाहिए होगी? The energy of one photon.
Time.
H bar omega. Right? अब बताओ।
A cross-sectional area and A is the height of the cell. जो आपने diagram में use किया है। यहाँ पे A cross-sectional area और H height of the cell.
H कुछ भी नहीं है, ये n है। Number of atoms. This is the density of the vapor. So this would become, so if I put P absorb, suppose this is the differential power absorbed, dP. So dP absorbed over dZ, this is going to be equal to gamma N A H bar omega. So this is the energy that is removed from the beam. And you want to find out the energy per second. So you want to find out the energy removed per unit area, that is the loss in intensity. So the loss in intensity, dI over dZ, will be this thing divided by the area, cross-sectional area, with a minus sign, because this is a drop in intensity. So this drop in intensity is given by the photon scattering rate, n and H bar omega. Alright? Now, another thing that you could do is express this in terms of we do know another thing, that this gamma, this photon scattering rate, is actually equal to S naught over all of this. Correct? proportional to an intensity, right? S naught is proportional to an intensity. So if I take this photon scattering rate, in the weak field limit, this gamma is, this S naught will be much smaller than this term, right? If S naught is small, so we'll just have S naught in the numerator, right? When S naught is in the numerator, we know that S naught is proportional to an intensity, right? So in the weak field limit, this is proportional to some constant of proportionality alpha intensity. Okay? In the weak field limit. Okay? The weak field limit, the photon scattering rate is proportional to the intensity. Okay? So in that case, what we could do is we could replace this. This becomes proportional to an intensity. So my di by dz is going to be proportional, equal to minus some alpha n h bar omega I.
सचिव यहाँ I है वो incident
Intensity. In fact, this intensity is at any value of z, because the photon scattering rate might also change as you go along. This length of this object. So this is the relationship that we have in front of us. Okay, in the weak field limit case, remember. So as you go along the length of this object, di by dz varies, the negative sign proportional to I. So now how do we solve this? Yes, please. ये एक ही है. So how do you solve this? What's the solution to this? It's a decaying exponential. So I becomes a decaying exponential. I, as a function of z, is some incident intensity at z equals 0, which is the intensity at z equals 0, exponent minus alpha n h bar omega z. Correct? It's a single derivative.
So ये जो I of z है ये incident intensity है.
नहीं, this is the intensity at some section g. Yeah, so this is, we've broken down this big chunk into small dc. So this is the I at any z, and this varies along system, right? So this is my decaying electric intensity of radiation. So I can call all of this alpha h bar omega e minus some, this is generally called the cross section, sigma n z, right? So the intensity at some z, decay. So if I make a plot between the intensity inside the medium at some z, where the density is constant across the medium, at some z the intensity drops exponentially. And this is absorption. This is due to photon scattering. Okay, in the weak field limit. Okay, remember this. This is the weak field limit case. So this has generally become a law. This has gained the status of a phenomenological rule of thumb. You pass light into a medium as you progress along the length, the intensity drops exponentially. This is also called the Lambert-Beer law. So if in this case you not only see photons from the side, but if you look at the entire beam of light that is going inside the medium, its intensity is exponentially dropping as you go through the system. And the rate at which the intensity drops is proportional to alpha. And that alpha is proportional to the photon scattering rate. Higher the photon scattering rate, the intensity will drop, higher will be the absorption. Faster will be the absorption. So this is how a gas of atoms absorbs electromagnetic radiation. It can also be described through the phenomenon of saturation and the semiclassical treatment of radiation interacting with the quantum two-level system. That can also describe absorption. So now what we're going to do in the next lectures, starting from Thursday. I'm sorry I couldn't take last week's lecture, and shall try to make up for that. We're trying to start quantizing the electromagnetic field. So I want to ask you if everyone is familiar with the idea of the harmonic oscillator. Right? So you all know the quantized harmonic oscillator. You know that its energy levels are quantized, it has a parabolic potential, and you know the creation and the annihilation operators are. So what we're going to do is we're going to express, so what is an electromagnetic field? Electromagnetic field has 6 variables at any point in time and space. The 6 variables. 3 electric fields, Ex, By, Ez, and 3 magnetic fields, Bx, By, Bz. So at any point in space and in time, there are 6 variables that we have to cater for. Okay, and what we'll see is that the electric and the magnetic field, they become operators. And they correspond to position and momentum operators of a harmonic oscillator. And they obey certain commutation relationships. The same commutation relationships as exist between position and momentum. Right? And they are incompatible observables. So light in this sense acts like a harmonic oscillator, with the electric and the magnetic field operators acting as position momentum operators. And out of these position momentum operators you can then create, through their superposition, creation and annihilation operators. And those objects, creation and annihilation operators, are creating photons or annihilating photons. So photons become excitations of the harmonic oscillator. Right? So this is how we start looking at this treatment, this quantized treatment of light. And then we'll describe this quantum state of light, which is called a Fock state, or number states. And then we'll describe coherent states. And then we'll describe squeezed states, amplitude squeezed and quadrature squeezed states. Right? And so then we have this quantum description of light. And then we'll see how this compares with classical and chaotic light. And what tools do we have at our disposal to make this comparison? We have a tool called the second order correlation function. We'll find out what the second order correlation function is. Right? So we'll do some statistical treatment of detection outcomes from quantum light and classical light. And in the process we'll describe what is meant by bunched light, anti-bunched light, and what are the probability distributions for detection of photons, Poissonian, sub-Poissonian, and super-Poissonian. So the next 3 or 4 lectures will kind of focus solely on light. We'll take matter away from the picture. We'll focus solely on light. And then we'll come back with quantized light and quantized matter to develop the Jane's coming model. We have a full quantum mechanical treatment of photons interacting with atoms. Okay, so please, I'm making the homework very carefully. So please do the solution very carefully and look at each every bit of it, because only then can you understand what's going on.
The solution कब तक आएगा मुंबई?
मैं आज प्रिपेयर करके